a series of talks that report on work done at the program, and I'm delighted to introduce the second of these by Angelica Babei, who will tell us about learning elliptic factors in elliptic curves.
Thank you everyone for being here, and thank you to the organizers for giving me the opportunity to report on some experiments that we did as part of the second number theory workshop, maybe 3 or 4 weeks ago. So this talk will be pretty heavy on the plots, lighter on the results, but I hope that I can make a good argument for why transformers can be accessible and easy to use and also useful for the research mathematician. We did have GPUs here, thankfully, as part of the program, but we could totally run these experiments on a personal computer GPU as well. So we did these experiments a few weeks ago together with Aaron Asaf, Edgar Costa, David Lauraduda, Coco Wang, and Yuan Li. All right, I will start with telling you a little bit about L functions. Now, if you were here yesterday during Edgar's talk, I really won't tell you much more than he did. But basically, the Riemann zeta function is probably the most well-known L function. We usually know it as this infinite sum, 1 plus 1 over 2 to the s plus 1 over 3 to the s, etc. This sum makes sense when you're taking s, if you're thinking over reals, greater than 1, then the sum converges, but it really doesn't make sense for s 1 and less, right? 1 plus 1/2 plus 1/3, etc. does not converge. However, the beautiful thing is that you can take this function and complete it over the complex plane. And here's a beautiful illustration of what this completion kind of looks like. In that sense, you get a very nice complex function that extends to the complex plane. It will restrict when s is greater than 1. So I guess that would be on this side to that infinite sum. But on the other side, it's an interesting completion I really won't tell you much about. Then the Riemann hypothesis says that, well, you're getting these kind of trivial zeros on the real axis, but it's extra zeros, here's some red dots, on the line x is equal to 1/2 that are really interesting. And the Riemann hypothesis says that those are really the only interesting zeros that exist. All right, the other cool thing is that it's an infinite sum, but you can really write it as a product over primes. And although the Riemann zeta function is kind of the L function that we know we have seen most often, there are many other functions that behave like it, that have their own Riemann hypothesis type of scenario, and those are called L functions. And these L functions come from interesting objects such as number fields or from geometry, from elliptic curves, etc. And that's what I want to tell you in the next slide about L functions coming from elliptic curves. There are many ways to think about elliptic curves. Probably the most down-to-earth way to think about them is that they are given by this nice cubic equation in x and y. Then and I guess here are some examples of elliptic curves, well, mostly over R. And given an elliptic curve, you can obtain an L function the following way. The L function itself is a product over primes, and then basically at most, well, okay, except for like a handful of primes, these local factors, which are the Euler factors that we're going to learn. So these local factors are given by this nice expression, and the AP of e's, these are the quantities that we'll try to learn in the experiments that I'll report on. These AP of e's are equal to p plus 1 minus the number of solutions of the equation defining the elliptic curve modulo times b. So it's very easy to compute. All right. So we're having these L functions, and the experiments I'll tell you about will be learning these AP of E given information about the elliptic curve. All right. There are 3 series of experiments that I will tell you about. The first series of experiments is kind of something that you might want to do, all right, if you have, write the equation describing the elliptic curve, it comes with a bunch of coefficients, and this is what we call a Weierstrass form of the equation. So if we're giving it the equation or the Weierstrass coefficients, A, B, C, D, and E, can it learn those Euler factors, A, P of E? If you're here at the previous talk, you've seen that this is not a trivial thing to do. Okay, for classical neural networks, there's really no hope of doing that. And one of the reasons why is that when we're computing A, P of E, we're solving equations modulo primes P. And maybe for us, it seems that 11 is close to 10, right? But from a number theory perspective, 11 is really closer to 121. And then a transformer can kind of hopefully learn some interesting embeddings that would make sense with those kind of metrics. The other class of experiments that we ran was, okay, now let's fix a prime P. Can we learn that AP of E based on nearby factors? And we kind of divided this up into two series of experiments. Can we learn the parity, whether AP of E is divisible by 2 or not? So it's really just a binary classification. Also based on, are the other Euler factors near it divisible by 2 or not? And then finally, all right, can we feed it all the data, not just the parity, but can we feed it the Q of E for nearby primes and learn A97? And the idea here was that, well, ultimately the transformer that we're using is kind of a sequence to sequence model. So maybe if we can learn A97, maybe we can learn A101, A103, etc. All right, so before I tell you about the experiments, are there any questions about the introduction so far? Yeah, Marina?
So are there any theorems saying that, like, if you definitively know, like, the first, like, n APs, then you know all of them? Is there something like a Sturm-Bound kind of thing?
That's a good question.
Yeah, that's the square root of the conductor.
So if you know the APs up to the square root of the conductor, then
Yeah. Even mod 2. Even, well, you know the mod 2, you know.
I'm saying the Sturm-Bound also works for larger function.
okay.
All right, so the main tool that we used was Francois's code for end-to-end, which we're immensely grateful to him for making this available to us. It's basically an encoder decoder transformer that's available at Francois's GitHub. And it's very easy to use. It has a very good README that can tell you how to initialize things. The tokens are embedded in a 256-dimensional space. It also has a positional sinusoidal embedding. All right, and both encoder and decoder have 4 transformer layers, and each of them has a single feed-forward layer of size 256. It uses Relu, but you can have some customization there. Also, each transformer layer has 8 attention heads, right? And the idea is that end-to-end is really geared for integer sequences to integer sequences. And mostly we used kind of the default parameters in the model, except for some cases where I'll tell you exactly which learning rate, which batch size, etc. we used. All right, so for the first series of experiments, we're giving it 5 coefficients, A, B, C, D, E. Can we learn those Euler factors? The data set that we used was one with 2 million curves that were generated by kind of sampling uniformly at random these A, B, C, D, E coefficients. So in particular, we're not necessarily getting minimal models. We used the Atom optimizer. The learning rate, except for one experiment, was 10 to the minus 4, and we used the default batch size of 32.
So,
yeah.
So this data set is not like all elliptic curves up to some conductor.
That is correct.
So what was the largest conductor in this data set?
I actually don't know. Yeah. Oh, also, we sampled the Weierstrass coefficients in this interval because one of the parameters in int is the base in which you're encoding your integers, and the default base is 1000, but you can change that a little bit. All right, so what have we learned? Yeah.
So the integers are represented in the binary representation. So when you give it to the transformer, so is it like you take the binary representation for the ABCD?
Oh, so we're actually just giving it in base 1000. So like 985 is 985. Yeah.
So do you think like, so can you encode like in some other form where basically this number you said like that 11 is closer to 121 versus this, so can it have a better representation of the input to the transformer?
Oh yeah, for sure. So we haven't really tried that, but it's not clear how much the results will depend on the base itself. So Francois did some interesting experiments learning the GCD of two numbers, and there the results were very dependent kind of on the base which you're encoding. So we can totally try different bases. We can also try to encode the coefficients in different ways as well. Yeah. Thank you. So what we got was that the transformer did exceptionally well for the first few primes. Okay, you'll notice I don't have A2 here because 2 is usually weird prime. Okay, so we kind of ignored it. But for A3, A5, and A7, it did eventually learn up to like almost 100% accuracy. The really cool thing is that you can notice, and I'm sorry, it might be a little bit small, but in each of these cases, especially for A5 and A7, we can see that it kind of stalls and then it has like these step learning. For A5, same thing for A7. Now, the data set itself had 2 million examples. The epoch size was 300,000. All right, and here you can't really see it, but we ran it with like 140 epochs, a few hundred. So it really has seen the training set many times over. So these kind of steps could be due to grokking, where the model kind of goes past memorization to actually understanding what's happening in the background. All right, it can really learn the pattern. So we don't really know. We think it's probably grokking here. It'd be interesting to actually see what the model has learned. And that's for the small primes. Yeah.
Can you just tell me what's the range of the y-axis?
Y-axis is this one? Okay. So it goes from around like a 12% probably to 100.
You don't need to be precise. So I just want to know the
Yeah.
bottom. So can you get it close? The same.
This one's like 22, and this one it's like maybe 15.
Okay.
Yeah.
So it starts around 20% and then jumps.
Yeah, so I personally didn't do these experiments, Coco did, but I think what's happening here is that it kind of starts with how many options you have. So it's something that I didn't tell you so far is that there's really finitely many options that AP can take. There is a bound called the Hasselbalch that it tells you that the AP sub E is between -2 root P and 2 root P. So it's really very few options, especially for the smaller primes. So this is probably kind of depending on which one was most prevalent.
Or even just randomly guess, you expect to be right about 12% of the time. So
Right, yeah. So it learned pretty well for the first few primes. And then it gets stuck. Immediately once it gets to A11, it just gets stuck. For A11 and A13, what happens is that it kind of gets stuck in just choosing one of the options. Something that could get the model unstuck would be maybe modifying the learning rate. And this is what we tried for A11, changing that learning rate from 10 to the -4 to 5 10 to the -5. So, half it. And it wasn't just choosing one of the options, but it wasn't really learning either. But here with just 10 to the -4, it just kind of bounces between the options. So really, I'm saying learning to 100% accuracy doesn't happen, but it's not clear if any learning happens here, really. So we wonder, is this a learning problem? Maybe we can do some hyperparameter tuning, maybe we can do some other clever things that will help it learn, or is there something really more fundamental obstruction to learning these coefficients? And we don't know.
I mean, this problem is very obvious for low problems. It's not quite linear, but you could imagine a circuit that actually computed it, because you could just scan through all the values of x and test, the equation. And the computer, again, it can learn any mod p of the input tokens for the coefficients. So a question you can ask is to try to make that circuit precise, and then what you might find is that of course it gets bigger and bigger with the size of the prime, and perhaps goes to some power, and then these are just too big. Once to get up to t equals 11, so taking more parameters down,
Right.
some minimum number of parameters where it would start to work.
Right, yeah. Yeah, maybe if we throw more resources at it, maybe things will work.
But there's a quantitative, there's a
Yeah.
prediction that you can make.
That's a good point. Yes?
And I guess like you are learning a separate neural network for each prime.
That is correct.
So
Yes.
if you start, like, do you think there is a better, like, say you learn a single neural network, so you have two inputs. One is like the part for the particular prime, and like they could be learning across different primes, which could help you like to get a curriculum. Does that, like, I don't understand the math part of it, so maybe I'm missing some.
I mean, honestly, like any suggestions are really good because we don't really know what to
Like,
really
so
try.
if you have a single neural network which is for doing, for example, 357. Maybe like it has much more, like it can learn something general out of like these things, and then it helps to climb on other ones.
Oh,
Was what I was thinking.
right. So if I'm understanding you correctly, maybe you're saying like there might be some interplay between A5 and A7, something like that. I mean, that could be. That will bring us to the next experiments where we're basically kind of we're feeding it nearby Euler factors and trying to see what it can get from those as well. So we haven't tried that for the Weierstrass coefficients experiment, but that would definitely be worth looking into. Thanks.
What's the accuracy for A11? Highest two.
Around like 17.8, maybe.
17.
Yeah,
17.
17.
17.
Yeah, it was really funny how it just really broke down. But it could be maybe just not enough parameters. Yeah.
But also the theory is also like for the other ones, you kind of just learn the table, right? Because in some way, if you know the Weierstrass coefficients model, whatever prime you're looking at, then answer of getting the AP on the nose is. So the question is like, can it store a big hash table behind the scenes and just memorize that?
Right. I mean, probably what's happening, right, when you're looking at those steps that it's taking.
Or that's like the early stage of this is evidence that is even more.
Yeah.
But again, there really, I think, is a pretty simple implementation of this function that you can imagine to know what it encodes. So that's.
Okay. All right, so I'll kind of speed through the second class of experiments, where now we're feeding it nearby Euler factors and trying to learn, A2, A3, etc. But modulo 2. Okay, so it's really kind of like a binary classification problem. So we looked at a few different primes. We looked at the first few primes. 2 and 3 were really the hardest to get off the ground. We had to change learning rate there a little bit to get it on top, basically from choosing just one of the two options. The data set that we used is a data set of elliptic curves of conductor. I didn't tell you what conductor is, but it's just one way to kind of order the curves up to 10 to the 6. This is not a complete set as far as I know, and it has 3.5 million example curves. All right, we use the atom optimizer. The learning rate was halved from the default, so 5, 10 to the minus 5, and we use batch size 32. Now, this will be a little bit confusing. So I'm not sure how much I want to tell you about this, but basically, if we're just giving it a sequence of zeros and ones, you really kind of just have two words, right? 0 and 1. Yes, you have positional embedding, you have attention mechanisms. So ultimately, the model will learn, but maybe if you want to try to interpret it, it might make sense to give it more than just 2 points. Okay, so what we did was that we concatenated the prime to the AQ or AP mod 2. So we got 48 words instead of 2 to begin with, because
So you're just giving it a series of numbers which are 10p plus a sub p, not 2?
sorry, can you say that again?
So you're just multiplying p by 10
Oh,
as
yeah.
a sub p?
No, so
A sub p mod 2, yeah.
yes, it is a sub p mod 2. Yeah, so
It's just a different code.
I suppose, but then the program has to discover that it's not 10. That it makes 10, that there's a factor of 10 in there, not part of the math.
But it doesn't start out knowing much about the numbers anyway, so it's just 1,000 tokens, so has to learn all those things anyway.
yeah, so mathematically, this is a weird encoding, but if you just treat them as words, eventually.
Okay, so you're saying these are not actually numbers at all, they're just like flags or whatever.
Yeah, these are words. Like, it doesn't really know that these are numbers, these are words. Yeah. We know that they're actually numbers. The computer doesn't know that yet. All right, and then it's a binary classification problem. It just takes, it gets out AP mod 2. All right, so these were kind of the different primes that we tried. Basically, higher primes gave better accuracy. The one on top is A97. It got up to like 92% accuracy. Then this is A31. So we skipped a bunch of primes on the way. Then this is A11, A7, A5, and this is where the A2 is kind of weird. It jumped ahead of A3. And initially I thought that this is maybe something to do with the C, the random seed at the beginning, but we managed to basically reproduce this. A2 kind of like jumps ahead of A3, which could have to do with the fact that 2 is a weird prime. All right, so it can do pretty well for larger primes, but for A2 and A3, it's really struggling to get, even up to like 70%. But the higher primes are doing a little bit better.
Do you have an idea why that happens? Why higher primes, bigger primes, better?
I do not know.
I guess why 2 and 3 would be hard, just because I think bad primes are gonna, most of the elliptic curves in the data set are gonna have to have reduction in 2, and that's just gonna make things very different. Why 97 is better than 31?
Well, the interesting thing to see is that you can extrapolate. These are all look like they have the same functional form, so you can just extrapolate and say what is the ideal accuracy, predict that, and then just plot the prime on the x-axis and this ideal accuracy on the y-axis, and you probably get a nice curve then. That would be the thing. So.
Oh yeah, for sure. So sorry, it doesn't quite hit 100. 100 would probably be somewhere here, but it goes like the highest accuracy is around 92%. I think it's actually 91.5.
I think maybe a reason for the A2 is to show what Bruce said, but also like one problem is like if I give you a sequence of APs guessing the next AP, by the time they get determined, sequence is like already fixed, that is small enough. Well, if I give you all the later APs, then he asks you what's the A2. It's not obvious there's only one answer. So there might be more options for the small primes.
Hmm.
Still find it very striking that it can get it 97. We're asking the wrong question. Why does it do that at A2? How does it do?
Yeah, exactly. It's clearly there's something there that you should understand.
I don't
Begun to
know that you
discover
can easily
something.
memorize.
No,
Maybe there's only a small
no,
number.
no, there must be some sort of-
I think you can. So it's
to keep it so.
It's a P mod 2 that tells you basically something like some factorization of the cubic polynomial module P that you
But we're not giving the polynomial, we're just giving like the,
Understand?
If you're only giving a dear one, I mean, basically, if it was memorizing, it would have to be memorizing like all the mod 2 Galois solutions, so.
Yeah.
Do it for all the primes, and then make this and try also a model where it tries to fit several, the APs for several primes at
Some kind of
once.
murmuration effect for.
Help each other a little bit.
For the L function.
Right.
Yeah, there's obviously something here you have to keep working on.
So because I don't want to go too much over David's time, I will jump over the next few things. So some things that we tried, adjusting learning rate, I told you about vocabulary, etc. But ultimately, because A97 did so well, we're thinking, can we actually learn not just the parity, but can we learn A97 itself? So, all right. We tried some experiments. You'll see later why I did this, but we basically fed it the root number or the parity of the rank because something looked like maybe murmuration, so it was curious to learn if that's what it was learning. But basically now we're feeding it all of the AQs up to 97. And we also concatenated as part of a word, you know, the prime itself. But it was actually more the position of the prime just to make sure to kind of limit the vocabulary that it had to learn. That was for interpretability reasons, and we'll see some plots later. We tried a few different learning rates. The best one was 310 to the -5. Higher learning rates were kind of plateauing sooner. Lower learning rates weren't really getting quite there. So it did up to like 45, between 45 and 46% accuracy. Now, that is actually pretty good, given the fact that it had to distinguish among 39 choices. The most prevalent were 2 and -2 at 8.4%. So it does well, way better than chance at 45%, but the downside is that there doesn't seem to be any hope that you can generate, you know, A97, then A101, A103, etc. if you just have like less than 50% chance at every step.
The cross entropy is what you want to.
Yeah, so I think, yeah, I have those plots. I don't remember exactly. Oh, yeah, but we're still a little bit far from keeping to generate them. Okay, now we wanted to see, well, what was it actually predicting? So the way to read this is that you're kind of fixing a target on the x-axis, and then going up, you see kind of a proportion of what it chose. So if we're here at -15, most likely it actually chooses the right option among all the other options. If it doesn't choose the right option, the next most likely is actually it's negative. Okay, so this diagonal is kind of perfect prediction, and then the anti-diagonal is, you know, the negative. So usually it chooses the right option among all the other choices. If not, it's the negative, except for this case. But I don't think there's anything special here. It just might have to do with evaluating this particular test set. Okay. The other interesting thing is that the density of choices between, you know, -AP and AP is slightly higher than the density of choices outside of that interval. So that's why we're thinking that maybe it was murmurations. So we were we fed it the root number as well, but we would basically still have the same kind of interesting results.
So is the accuracy on the absolute value of AP then would be well over 50%?
Yeah, I think it got to like 65. Yeah. Yeah, so that was pretty neat.
Now, do you know if you multiplied AP by the root number, would it do any better, or would that just be? Because that's sort of the right variable for murmurations, it's root number times AP.
But because we fed it, you'd think that it would kind of like learn it. Oh.
It's so bad.
should try to multiply, or just try to do the absolute value and see if that's better.
Right.
Yeah, training on the absolute value might help it be better than what you're seeing.
Yeah, because I just kind of aggregated the, but yeah, training it actually.
Still, I find 45% very impressive. I would want.
There's clearly a lot here.
It's great.
Well, wait until you see these ones. So I'm sorry, you probably can't see them in the back. I didn't realize it would be so small. But basically we wanted to see, can we interpret what the model is learning? So we would feed it input sequences, okay, and then extract the internal learned representations of the model. And here we have the encoder, okay, because the encoder had those many more tokens. So here are the internal presentation at the first and the second transformer layer. So at the first one, it kind of roughly divides up the token based on the prime that they belong to. So the different colors are the tokens for different primes. So I think here in dark blue, it's for the prime 67, and here it's for the prime 89. Okay, the other interesting thing is that it also seems to divide at least these two by divisibility by 4. So here are, well, actually mod 4. Here are the A89 that are 1 or 3 mod 4. I think this is where it's completely divisible by 4, and here where it's 2 mod 4, or it might be the other way around. And kind of something similar here. There's one blob, another, and then a third. But the ones here are kind of more mixed. Now, the second layer seems to really divide the tokens based on divisibility by 2. So these are mostly 1 mod 2, and here are mostly 0 mod 2. So that, I don't know, but that could potentially explain why guessing A97 mod 2 was so successful. Maybe because the model itself kind of learns to look at the AP's mod 2, but that's just speculation. Okay, so I think this is where I stop, but thank you very much for listening.